In this lesson, we'll discuss derivatives of trigonometric functions. And to start with, what is a formula for the derivative of sine of x? Here I have a graph of y is equal sine of x, and to figure this out, we're going to guess the derivative by sketching its graph. Now, if you remember, when it came to sketching graphs of derivatives, I broke it up into three pieces, whereas 0, negative, and positive. So to start with, there are 1, 2, 3, 4 places where we have horizontal tangent lines, and therefore at these locations, the derivative, which I'll graph in red, is 0. Here, 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 and here. Again, the reason for this is, if you're looking at your function, wherever it is horizontal, even for just a moment, the derivative is equal to 0 at those places. So everywhere else, it is either positive or negative. So from here to here, the derivative is either a positive value or a negative value. Since the function is increasing, the tangent lines have positive slopes. Therefore, between here and here, I'll note that the derivative must be positive. From here to here, the function is decreasing, so the derivative is negative. And then from here to here, the derivative is positive again. And likewise, from here and on, the function is increasing, so the derivative is positive. Here the function is decreasing, and so the derivative is negative. Let's start by trying to graph what's going on between here and here. So the derivative is, it starts at 0, it becomes positive and more positive before dropping back down to 0. If I try to sketch that, you'll get something that looks like this. The derivative becomes more and more positive, and then it goes back down to 0. From here to here, the derivative starts at 0. It becomes more and more negative before going back to 0. So it should look something like this. And then lastly, from here to here, the derivative is positive and getting larger, and so it looks like this. Again, over here, the derivative starts out at 0. It becomes more and more negative before going back to 0. So if I sketch the numbers like that, I get this. And lastly, in this region, the derivative is positive before going back down to 0, and its graph would look like this. So what function resembles the graph of what is in red? That function is cosine of x. If you graph cosine, it starts out at 1, it drops down to -1 at pi before going back up to +1. So this is a nice rule that we now have. The derivative of sine will equal cosine. So here in example 1, we can now use this rule in combination with product and quotient rules. So for example, what is the derivative of x to the 5th sine of x? To take the derivative of this thing, I see we have a product of two functions, x to the 5th and also sine of x. So the product rule says it's the first times the derivative of the second, which we now know is cosine. Then we add on the second, which is sine of x, and multiply that by the derivative of the first, which is 5x to the 4th. So unsimplified, here is the derivative of this function, and we can do that now that we have a formula for the derivative of sine. In the rest of this lesson, we'll look at cosine, tangent, and their reciprocal functions and figure out formulas for the derivatives of them. So starting with cosine, what is a formula for its derivative? And again, here I have a graph of cosine. Maybe the answer will be simple and it'll just be equal to sine. I'm putting a little space here for a reason, but what we're going to do is try to sketch the graph of the derivative of cosine and see if it is something like sine of x. Again, the places where it's equal to 0 are here, 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 and here. At these locations, there's a horizontal tangent line, and therefore the slope is 0, and so I can graph the number 0 for the derivative. Now, in between these values, let's say from here to here, the function is decreasing, so note that the derivative is negative. Here it is increasing, so I know the derivative is positive. Here the function's increasing, so the derivative is positive. And then here the function is decreasing, and so the derivative is negative. If I quickly sketch what that should look like, negative values from here to here look like this. And then if they become positive, it would look like this. If we have positive values here, this is what the derivative would look like. And here we have negative values. So here's a quick sketch of the derivative of cosine of x. And the question is it equal to sine? The answer is, of course, no. The graph of sine starts at 0 and ends at 0 here, but it's first positive and then it's negative. In fact, the graph that we have here is the reflection of that. Said another way, it is negative sine of x. So unfortunately, cosine doesn't have a derivative of just sine. In fact, the derivative is negative sine of x. We now have this as a rule, so now if it shows up in taking the derivative of some function, I know how to deal with it. So here, what's the derivative of e to the x times cosine of x? Well, again, we have a product of two functions, e to the x and cosine, and therefore I can use the product rule, which says it's the first times the derivative of the second. The derivative of the second is negative sine of x. We then add on the second, which is cosine of x, and multiply by the derivative of the first, which is e to the x. And this is the derivative. It's unsimplified. I'm sure we could maybe factor it a little bit, but I'm going to leave my answer just like this. All right, so great. We have the derivative rules for sine and cosine. That leaves, well, tangent, and then also all of the reciprocal functions like cosecant, secant, and cotangent. I want formulas for all of those things. Let's start with what is the rule for the derivative of tangent? Now you can see I don't have a graph here because I don't want to try to sketch the graph of the derivative. I'd like to use information that we have to prove a formula for this algebraically. So what is the derivative of tangent? Well, it'd be good to know what the definition of tangent is. Tangent is defined as sine divided by cosine. And for this reason, you can actually write this as the derivative of sine of x divided by cosine of x. So to take this derivative really means to take the derivative of this. Why is it helpful to write it this way? Well, it's a fraction, and we have a quotient rule that tells us how to take the derivative of that. And also, in just the numerator and the denominator, I know how to take the derivatives of both pieces. So I'll combine all of this together. The quotient rule says if we take the derivative of a fraction, it's the denominator times the derivative of the numerator, and the derivative of sine is cosine. Then it's minus the numerator times the derivative of the denominator, which cosine goes, we saw, to negative sine. And then this whole thing is divided by the denominator, which is cosine of x squared. So that's supposed to be sine of x there. This is probably not the best way to write a rule. It'd probably be better if this thing were simplified. So I think we should take a minute to just try to simplify this as best as possible. So let's see. Well, here we have a cosine times a cosine, which is cosine squared. It's customary to write it like this: cosine squared x. So you put the squared after cos. Next, we have minus a. Well, this whole thing is going to be negative. Times the negative will make it a positive. So we get positive, and if we have a sine times a sine, we'll write that as sine squared of x. And this is all divided by, and I'll also write the denominator as cosine squared x like this. So it looks a little better, but we can take it one step further. There is a very important identity. That identity is sine squared of any angle theta plus cosine squared of that same angle is always equal to 1. This is always true. Doesn't matter if I put theta or x. This entire numerator is equal to 1. So this is really 1 divided by cosine squared of x. And we can do even better. Like, this is a fine way to write the rule. However, there are reciprocal functions for sine, cosine, and tangent. I'll make note that secant is defined as 1 over cosine. So if you see a 1 over cosine, you can really replace that with a secant. And if you're squaring them, then you can square it here as well. The answer to this is also expressed as secant squared of x. This is typically how the rule is stated. The derivative of tangent is secant squared x. That way we don't have any fractions, and we can leave it just like this. All right, let's try that in example 3. I want to differentiate tangent of x divided by x. I have a fraction, so I've got to use the quotient rule. The quotient rule says it's the bottom times the derivative of the top. And the numerator is tangent of x, so its derivative is secant squared of x. Then it's minus the top, which is tangent of x, times the derivative of the denominator, which is 1. And this whole thing is divided by the denominator squared. Again, this is unsimplified, but in terms of taking the derivative, this is what it is equal to. All right, so this is fantastic. What we have so far are rules for sine, cosine, and tangent. Their derivatives are cosine, negative sine, and secant squared, respectively. But like I said, there's 3 other trig functions as well: cosecant, secant, and cotangent. Just recall the definitions of these things. If you see cosecant of x, by definition, that is the reciprocal of sine. If you see secant, by definition, that's the reciprocal of cosine. And here we have cotangent. You could write that as the reciprocal of tangent, 1 over tangent, but it's customary to do this as not sine over cosine, but cosine over sine. So here are the definitions for cosecant, secant, and cotangent, the reciprocals of sine, cosine, and tangent. I have stated the rules for all 3 of them. The derivative of cosecant of x is negative cosecant x times cotangent x. The derivative of secant of x is secant x tangent x. And then for the derivative of cotangent, that's negative cosecant squared x. What I'd like to do is prove one of these rules, and I chose the derivative of secant of x is equal to secant tangent. And we'll go over that proof together. And I recommend that you try proving the other 2. So to start with this one here, I don't think it's going to be too difficult of a proof. So what is the derivative of secant of x? What we'll do is replace secant with its definition. And by definition, secant is 1 divided by cosine of x. How do we take the derivative of this thing? Well, we have a fraction. That means you can use the quotient rule. And note that individually, we can take the derivative of both the numerator and the denominator. So starting with the quotient rule, it's the denominator, which is cosine of x, times the derivative of the numerator, and the derivative of 1 is 0. So that's nice. That'll simplify really nice. Then we subtract the numerator times the derivative of the denominator, and the derivative of cosine is negative sine of x. And this whole thing is divided by the denominator, which is cosine of x, all squared. We should be able to simplify this whole thing so it looks just like this. So to start with, I don't need to write this at all. This whole part's just 0. I have a negative times a negative, which is a positive, and I don't need to write that 1. The entire numerator is just sine of x divided by, I'll put cosine squared x. Now, to make this look more like this, well, a sine over a cosine will give me tangent, and secant is 1 over cosine. I'm thinking I'm going to take the denominator, and I'm going to write it as, I'll put it as cosine times cosine. Because this way, you can actually break this up into 2 fractions if you put a 1 here. This is equal to 1 over cosine of x times sine of x over cosine of x. If you multiply the denominators and numerators, it would take you back to this, or simply back to this. Now, 1 over cosine, by definition, is secant. Sine over cosine, by definition, is tangent. And we have it. This is secant x times tangent of x. So that proves this rule here. The proofs for this and this would be very similar. You'd start by writing cosecant as its reciprocal and taking the derivative of this using the quotient rule. And the same is true for cotangent of x. In example 5, I'd like to differentiate f of t, which is t times e to the t times cotangent of t. How would I take the derivative of this function? Since we have a rule for cotangent, this is now possible for us. It looks like I'll have to use the product rule because I'm multiplying functions together, but I'm noticing that we actually have a product of 3 functions. So before actually taking this derivative, I'd like to review the product rule and actually show you a shorthand notation for the rules. Let's start with this thing here. The product rule can be thought of as 2 functions being multiplied together, and then this prime means you take the derivative. I'll call my 2 functions u and v. If you remember what the product rule says, it's the first times the derivative of the second plus the second times the derivative of the first. You could write it like this. If your functions are u and v, you could put down 2 copies of them. You're adding them together. You take the derivative of one while leaving the other alone. And then in the next term, you just take the derivative of the function that you did not take the derivative of in the first part. So it has like a really nice flow to it. You copy down the 2 functions, you take the derivative of the first, leave the second one alone, leave the first one alone, and take the derivative of the second. Well, what happens if you have 3 functions being multiplied together and then you take the derivative of that? Is there a simple product rule for this? And it turns out the answer is yes. The pattern is you copy down the 3 functions, but you don't do it twice. You do it a total of 3 times, since there are 3 functions. And then in the first one, you take the derivative of only the first. So you put the derivative there, and you leave the other 2 alone. In the next part, you leave the first alone, but take the derivative of the second one. And in the last part, you probably guessed it, you don't take the derivative of the first or second, but only the last one here. This pattern holds true if you go up to 4 functions or 5 functions, but here I have a rule now for what to do if you have 3 functions being multiplied together. How can I take the derivative of this thing? I'll use this rule here. F prime of t is equal to, okay, here are my 3 functions, t, e to the t, and cotangent of t. And to start with, I take the derivative of just the first and leave the other 2 alone. The derivative of t is 1, and then I have e to the t, and I have cotangent of t. I then add on. All right, now I leave the first alone, and I take the derivative of only the second, so I get t e to the t and cotangent of t. And then lastly, I leave the first 2 alone and take the derivative of just the last. So that's t e to the t, and the derivative of cotangent, what was that? I believe it was negative cosecant squared of t in this case. So if you have 3 functions and you can remember the pattern to how these rules work, it actually doesn't take too long to write out the unsimplified version of the derivative. Very early in the semester, we actually figured out a couple of limits by using graphs and tables on a calculator. So here we have the limit as theta goes to 0 of sine of theta over theta. We verified this by looking at a graph and looking at a table of values, and we saw that this limit is always equal to 1. And the one here, where we have cosine of theta minus 1 over theta, we saw that this limit was equal to 0. Using these 2 limits, you can compute some more complicated limits. I'd like to remark something about this limit before moving on. If you have sine of something over that very same thing, the limit will always be 1. So, for example, if I said, what is the limit as x goes to 0 of sine of 7x over 7x, this is also 1. The rationale is 7x and 7x are identical. You're saying the thing here and the thing here are exactly the same. In fact, you could replace it by saying, let's let theta equal 7x. This limit becomes the limit of sine of theta over theta, which we saw was equal to 1, provided that theta goes to 0. While we're assuming that x goes to 0, that means 7x goes to 0, and therefore theta goes to 0 as well. So if you have that these 2 parts are identical, you can say that the limit of this whole thing is equal to 1 because we know that this is true. In part A, I want to figure out the limit as x goes to 0 of sine of 7x over actually just x. This limit will not be equal to 1, and the reason is there's no 7 here. It's actually just x. How can we use this thing to still figure out what the limit is equal to? There's a trick that we can do here, and it goes like this. In the denominator, we have just x, and in the top, we have sine of 7x. If there were a 7 here, the answer would be obvious. The answer would be 1. So what you can do is you can actually just put a 7 here. Now, this fraction is not equal to this one anymore. If you want these two things to be equal, you have to somehow balance this fraction. And there's a very simple way to do that, and that's by also putting a 7 in the numerator. This limit and this limit are now clearly identical because you can cancel those 7s and it will take you back to exactly this. How does this help us? Well, this 7 is not affected by this x, and you can actually remove it from the limit. You can write this as, this is 7 times the limit as x goes to 0 of sine of 7x over 7x. And since these two things are exactly the same, I know what this limit is equal to. It's equal to 1. I multiply that by the 7 that's on the outside, so it's really 7 times 1, and that means the answer overall is equal to 7. So this limit we could figure out because we knew this one, but we had to do a little trick. We had to adjust it so it looked like something that we could solve. Let's try this in a much more complicated example, like this one here. What is the limit as theta goes to 0 of sine of theta divided by 4 theta plus tangent of theta? How can I use this to figure out this limit? Well, the denominator is a lot more complicated than just theta. So one thing we could do is, I'll write down here, okay, this is the limit as theta goes to 0 of, in the numerator, I'm going to put sine of theta. Now, if this thing were divided by theta, so I'm including this, if this top was divided by theta, that's really great for this type of a limit because I know the top has a limit of 1. But if that's the only thing I do to this fraction, I've changed the value of the expression. Like these two things are not equivalent. But what could I do to actually make this equivalent to this? If I divide everything in the top by theta, I must also divide everything in the denominator by theta as well. This whole fraction and this whole fraction are now equivalent because I did the same thing to the numerator and the denominator. Here, let's simplify this a little bit. This is the limit as theta goes to 0 of, well, the top is, it's sine of theta divided by theta, but 4 theta over theta is just 4. That's good. And now I have plus tangent of theta over theta. Well, I'm going to replace tangent with its definition, which is sine of theta divided by cosine of theta. And we still have this theta here that's still in the denominator. So I have this thing. And this is looking pretty good. I know this limit's equal to 1. 4 will stay 4. And I'm really close here. Here I have a sine of theta over a theta, which again goes back to this limit here. But the issue is there's also this cosine. I think we can adjust this fraction a little bit to get our answer. I'll put that over here. This is the limit as theta goes to 0 of, so the top's all set. That's sine of theta divided by theta. We have 4. I'm going to write the next fraction as, I'll put this as 1 over cosine of theta times sine of theta over theta. Here's why this is helpful. Expressed in this way, this goes to 1, this goes to 1, based off of this fact. Nothing happens to 4, it stays 4. And to figure out 1 over cosine of theta, I can simply directly substitute 0 in place of theta. This will take us to our answer. The answer is, okay, well, the top is 1, so I'll just put a 1. We have a 4. We have a 1 plus 1 over cosine of 0 times 1. So I put 0 here, and I knew this limit was equal to 1. So what's cosine of 0? cosine of 0 is 1. So this is 1, this is 1, and the product is 1. If I add 1 to 4, we get 5. The limit, the answer is 1/5, and that is the final answer. The last thing I'd like to do in this lesson is actually prove that the derivative of sine is equal to cosine. We didn't quite prove it. We used a graph to make a guess at the answer, but I'd like to do a formal proof. To do this proof, we're going to have to use something called the sum difference formula for sine, and you might remember this from trigonometry. It tells you what to do if you're taking the sine of a sum or difference of two angles. And the rule says this is equal to sine of A times cosine of B plus or minus cosine of A times sine of B. Let's see where that shows up in the proof of this. So how do we prove that the derivative of sine is equal to cosine? We use the limit definition. The limit as h goes to 0 of sine of x plus h minus sine of x all over h. The reason I wanted to introduce this formula is because here we have sine of x plus h, and we can break this apart by using this rule, and that will be my next step. This is the limit as h goes to 0 of, what's sine of x plus h? It's sine of x times cosine of h plus, so if you have a plus sign, then you use the plus sign. We get cosine of x times sine of h. And then we subtract sine of x. And this is still all divided by h. Where do we go from here? Well, I see that here I have a sine of x cosine h, and here I have a sine of x. If I group this term with this one, it will allow me to factor out sine of x. So I think that will be my next step. All right, let's do that. This is the limit as h goes to 0 of, that's sine of x times cosine of h, and I'll put the minus sine of x next. And then I'll have plus cosine of x times sine of h. This whole thing is divided by h. I'm going to split this into two fractions. I'll put divided by h here and here. So that's like this and this. All right, so in this first part, I can factor out sine. If we do that, this is the limit as h goes to 0 of. If I take out the sine of x, what is left over? It's cosine of h minus 1 all over h. And I'm going to completely not only factor out, but remove it from the numerator and fraction entirely. Over here, I think I'll kind of do the same thing. I'll remove the cosine and leave sine of h over h in a single fraction. So this is plus cosine of x times sine of h all over h. So what does this equal? On the previous slide, I wrote down two important limits. The limit as theta goes to 0 of sine of theta over theta, we said that was equal to 1. And the limit as theta goes to 0 of cosine of theta minus 1 all over theta. And this is equal to 0. How does this help down here? Well, here I have sine of h over h, which is the same thing as this, except there's a theta. But this limit is 1. What's cosine h minus 1 over h? Well, since h is going to 0, this limit is 0. Nothing happens to this because there's no h in it. Same thing here, nothing happens to this. So you can actually take the limit. The limit is sine of x times 0 plus cosine of x times the other limit, which is 1. I don't need to write the part with 0 times sine. In fact, the only thing that is left over is cosine of x. And here's a more formal proof that the derivative of sine goes to cosine. And we did that by using the limit definition and also this trig identity.